Okay, so more max-min problems. You've got a piece of cardboard that's 10 centimeters by 7 centimeters. So if we draw a picture of this, and if you cut out squares out of the corners, and fold it up, you make a box. So if you have a piece of cardboard at home, you now know you could make a box out of it. Now, depending on how big or how small you cut those squares out, it's going to affect the volume of your box. If you cut too much cardboard out, you'll have a very tall, skinny box that won't necessarily hold a lot of stuff. If you decide you don't want to waste any materials, you will also get a box that's completely flat. And when you try to put stuff in there, like whatever your main collection of things at home is, maybe you collect, what are some collections out there? Collect coins, right? If it's just flat, you turn that and then they all fall out. So maybe you collect coins, or maybe you still have your Pokemon cards from way back when, and so you'd like to have a nice box to store them in. This is what you could do. You could cut out a square and then make that box. Now, depending on the size of that square, will give you different volumes. So you know volume is length times width times height. So if I cut out a square of size x, are you okay that my height will be x? What we're going to try to figure out is how long is our length, how long is our width. It's no longer 10 and 7. How long is our length now? Does it make sense that this green line right here is our new length? And this red line right here is our new width. It's going to be what? 10 minus 2x for that green length, right? And for our red length, 7 minus 2x. So what we were able to do is we were able to write an expression for the volume. Now here I said this would probably come up as a calculator question. If it comes up with a calculator question, you could now graph this, and in graphing it, find the maximum value. Some things from grade 12 pre-calculus about graphing this. Can you see that it's already in a factored form? So if you were graphing this without your calculator, or even if you were preparing to graph it with your calculator, you already know a bunch of x-intercepts. Can you see that there's an x-intercept at 0, at 3.5, and at 5? Does that make sense? If we multiply this out, I'm going to not have enough room in that bracket a little bit further. We'll get 70 minus 20x minus 14x plus 4x squared. Combine your like terms and multiply that x through. You'll get 4x cubed minus 34x squared plus 70x. So from last year, you would say, I know what a cubic graph looks like, and I have my x-intercepts. So from last year, you would know that this graph has to go up through this x-intercept, come back down, and then end going up again. This is just a rough draft using only the stuff that you learned in your grade 12 class. Using calculus, you could now figure out what this maximum point and this minimum point is, and you could also find the inflection point as well if you would like. Now, given the context of this question, only some of this graph actually makes sense. Okay? For example, Could you cut out a square with a negative length? So that means this section of our graph doesn't make sense, neither does this section of our graph. You can only cut out positive lengths. Does it make sense that I could cut out something for x between 0 and 3.5? Yes? Does it make sense that I could cut out something for x after 5? No, why not? The 7 value. The 7 value, if you cut out more than 3.5, is going to give you some issues because you're going to cut out more than you have. So this part also doesn't make sense. In fact, the only part of this graph that does make sense is between 0 and 3.5. Now, what we're going to do is we're going to solve this as if it was a calculator question. And if you were given this question as a calculator question, probably the quickest way to solve it would be to use your graphing calculator. You can easily type that volume equation into your calculator. So I'm going to go to my y equals. And I'm not even going to worry about the multiplied out because I might have made a mistake when I expanded everything out. I'm just going to write the 10 minus 2x, 7 minus 2x times x, just like we had it when it was factored. Now when I go to graph it, I'm going to start at -1 for my x min, but I know I don't have to go past 3.5. So I'm going to go up to 4 just so I have some nice numbers. I don't know how high I might need to make my y, well, my y min, I'm going to just have -1 just so I can see my y-axis. I don't know how high I'm going to need to make my y max. I could guess at this point. So let's do a bad guess and say it only goes up to 5. And then when we graph it, oh, it must go higher than 5. There it comes back down. So here is our x-intercept at 0 and our y-intercept at 3.5. If it's in radians, it's not going to matter here because we're not doing anything with sine and cos. So a couple of things I could do. I could keep guessing for my max or my min, or I could go to my table of values, which is right above your graph button, and just get a sense what's happening between 0 and 3.5. Notice it goes from 0 to 40 to 36 to 12 to -8. So it looks like just eyeballing it at 40 is the biggest one there. So when I go to my window, it might still be bigger than 40 in between 1 and 2. But it gives me an idea. Maybe I should set my y max to 50 and see if that's enough. It still might not be quite enough, but we'll check. Yes, it is. So here is a calculator question. It is a calculator question. You are able to do this unless the question explicitly says, using calculus, find the maximum. But if it just says, find the maximum volume that the box can have, we've now written that equation in. You can go second, calculate, number 4, a maximum. And it looks like it's really close to somewhere between 1 and 2. So I'm going to just pick 0 as my left and 4 as my right. That should give lots of opportunity to find that maximum. And there it is. Try that again. No, it's not liking me right now. At 1.35, the maximum is 42.37. Try this one. No. 2. All right. .38, 1.35. So that's using our graphing calculator. We find out the best thing to cut out as far as a square would be a square of 1.35. Our units are centimeters, so we should cut out 1.35 centimeters, and that will give us a volume, that's an ugly 3, of 42.38 centimeters cubed. And that's the biggest volume that you could make given that cardboard that you have. So if you're storing your coins, that would store the most coins. If you're storing your Pokemon cards, that would store the most Pokemon cards that you could have. Now, using calculus, it would have made sense for us to expand it. Ooh, that was fancy. Expand it like we did here to get the 4x cubed. And then once it's expanded, we could take the derivative, 12x squared minus 68x plus 70, and set that equal to 0. Now you might say, oh, I want to try to factor this. Well, I could factor out a 2. Yeah. Well, if I was using calculus, by finding the derivative and then setting my derivative equal to 0, I would find that tangent. I'd find the x where that tangent is 0, and that's going to be my maximum. So that'll help me find that maximum value. I can factor out a 2, leaving me with 6x squared minus 34x plus 35. And then going about trying to factor this looks like it would be difficult. So what do you do if you can't factor something? A quadratic formula. So again, you don't have a formula sheet, so this would be a thing that you would have to remember. Negative b plus or minus the square root b squared minus 4ac all over 2a. And using this factored amount right here, that would mean that my b is negative 34. My a value is 6. My c value is 35. And again, you would have to plug this into your calculator to see what you would get. Just doing some of the calculations separately, I'm going to do the 34 squared minus 24 times 35. That's 316. Now the square root of 316 is 17.77. 17.77 all over 12, which will give me two different answers. One of them will be 34 plus that divided by 12. Yeah, sometimes, like in this one, it might have said, using calculus, determine the volume. And so we have used calculus to get to this point. We still need our calculator to get to the next stage. So adding, I got 4.31. And subtracting, I get the 1.35. Now our calculus, by finding those, all that we've determined is 1.35 is a critical point and 4.31 is a critical point. Plugging in numbers into this, if you plug something less than 1.35 into that function, say if you plug in 0, you're going to get a positive number, meaning that our function was increasing. Plugging in a number like 2 will give you a negative number, decreasing, and then something after will be increasing again. So you would know that your maximum happens at 1.35. You might also know that your maximum happens at 1.35 because we determined earlier that the only things that made sense were numbers between 0 and 3.5. So the 4.31 wouldn't make sense for our situation. And so then 1.35 is the only possible answer. So that's how you could show using calculus. This question didn't say using calculus, so you would be able to graph it directly. but maybe you're not familiar with the graphing calculator that way, then this with the quadratic formula would be better for you. Yes? Yeah. How far? We got a right-angled triangle. A and B can vary, you can adjust them, but they always add up to 6. So an A here, now this is leading you to do the right thing. Often in a calculus question, you're just given that and then asked, what's the maximum area? But right now, this is kind of leading you. When you have a question like this, you're going to have to determine something to be x. They're suggesting make A to be x. You could have made B to C x, but because there's a relationship between A to B and B to C that they always add up to 6, we could make B to C y, but we could also just write B to C in terms of x. So what this means in terms of x is you write an expression for B to C, and the only variable you're going to use is x. You can still use other numbers, obviously, because it's not the same as A to B. But does it make sense that if they add up to 6, if this was 2, this would be 4. If this was 1, this would be 5. Right? How are you figuring out the 4 and the 5? Well, they have to add up to 6. Or maybe you took the 2 and said 6 minus 2 is 4, so that's what has to go here. So sometimes once you realize what would I do if I had easy numbers, I can figure out what I need to do if I put an x in there. So the length of BC is 6 minus x. So we can now try to figure out the maximum area of this triangle. Any guesses? Should it be 4 and 2? Should it be 1 and 5? 3 and 3? Any gut feeling? 3 and 3? Okay, we'll see if that works out. So we know that area is length times, or base times height divided by 2 for a triangle. We have our base is 6 minus x. Our height is x, all divided by 2. This makes this expression. Using calculus, to find that maximum, we could take the derivative, set our derivative equal to 0. That's how you find max and min questions. Can you see for this that you might want to rearrange this further? And if you have something all over 2, does it make sense that both of those things could be over 2? Sort of reverse of adding fractions. The nice thing about doing that is that makes doing our derivative a little bit easier. So now, what would our derivative look like? Well, it's just going to be 3 minus 2 comes out in front. That'll cancel out with that 2 on the bottom. Subtract 1 from the exponent, and you just get 3 minus x. Setting that equal to 0. This is not a calculator question. Will give us x equals 3. Years of experience. So we get x equals 3, so you were, in your guess of saying you thought it was going to be 3 and 3, you were correct. So now that we've got our value of x, let's just find the maximum area of the question. The max area will be 3 times 3 divided by 2, 4.5. Was it centimeters? Yes. So include your units, 4.5 centimeters squared. Base times height, 3 times 3 is 9, divided by 2, 4.5. So that question that we just did got us to think a little bit all in one variable, because when you're wanting to find a maximum of something and you're wanting to take the derivative, it's important that you have one variable. This one will lead you to that as well, but it's going to be more, this is more complicated. But again, the question is set up to lead you to that place so that you could solve for it. Again, sometimes later on in harder calculus questions, they don't lead you and you'd have to come up with this idea on your own. Can you set up an equation that only relates two variables instead of having three variables? So here we have a right circular cylinder. In other words, just a cylinder. There's a cylinder. Draw a picture of it with a radius of r and a height of h. So we know the radius, and here's the height. And we're told it has a volume of 54 pi centimeters cubed. So in a question like this, you're going to need to know some formulas about cylinders. Okay? Do you have your cylinder formulas memorized? Yes? Or do you know how they are made? Because I find if I know how a formula is made, I can memorize it a lot easier rather than if I'm just memorizing random numbers. So for example, for volume of a cylinder, volume is a formula that takes up space. The best way to describe how much space this takes up is to imagine taking a piece of paper and cutting out that circle as a base. And then another circle and add it on top and keep cutting out paper. And if you keep stacking up paper, eventually it will make a cylinder all the way to the top. Well, the volume formula for a cylinder is just that. It just says, take a circle and take enough of them and multiply that until you get up to the height, and you will fill that whole space. So if you can imagine that, then all of a sudden that formula is so easy to remember and so easy to memorize, as opposed to just remembering it from scratch. Same thing with surface area. Our surface area formula for a cylinder, can you see that there's a circle on the top and a circle on the bottom of your surface area? So when you have that, you have two circles, 2 pi r squared. You also have the surface area around the cylinder. So if we look at this cylinder right here, if you've ever had a can of soup that you've taken the labels off, have you ever taken a label off a can of soup? What shape does it make? It makes a rectangle. Okay? Fun thing to do is go home, go to your pantry, take off all the soup labels just to make sure that they're all rectangles, and say it was part of your calculus class. And when your parents go back and there's a bunch of cans with no labels on them now, then you'll have interesting suppers over the next little bit. Oh, I thought it was cream of mushroom soup and we're having kidney beans. Anyways, well, look, here's a rectangle. Sure enough, if I would wrap this around, it almost works perfectly to cover this cylinder. So how do we figure out that surface area? Well, we have to think of this rectangle. What do we know about that rectangle when you peel it off? Well, we know that the length of the rectangle, when you wrap it around, that makes a circle. And what part of the circle is that? The circumference. So we're going to have the length is your circumference. The width of that rectangle, how is that related to my cylinder? That's going to be my height. So there's your two formulas, both based on thinking about them and what they mean. And hopefully that helps you memorize them better by thinking of that. So what we're leading to in part B of this question is we're going to find the minimum surface area. This is an important question. This is an important question for all pop manufacturers in the world because they put pop into cans. Cans are cylinders. They want to fill as much volume as they can into those cans or they want to fill a certain amount, like 355 milliliters, but they want the can to be the right shape so that they can use as little aluminum as possible. Because when they make, and I don't know how many cans of Coca-Cola makes per day, but I think it's a lot. Because I don't think there's a place very few places in the world that you can go and not be able to buy a can of Coca-Cola. So right now, how many cans of Coca-Cola are there out in the world? Lots. And if you can even shave off 0.1 milligrams of aluminum, times that by the billions of cans that are out there, times that by the cost of aluminum, that's going to save Coca-Cola a lot of money. So these max-min problems are important to them. They want to minimize that surface area so that they can make the best shaped can possible. They make 1.8 billion cans a day. So if you just shave off 1 milligram off 1.8 billion cans, that's a lot of aluminum that you could save them. And that would make them happy because then they'll make even more money than they're making right now. And maybe I could become the first teacher sponsored by Coca-Cola and make millions of dollars in advertisements. They'll get rid of Tiger Woods and whatnot, and they'll just be the math teacher on their ads from now on. This video will go viral, and that'll be the start. Okay, maybe not. I'll get my hopes back down to normal. So it becomes an important question. And that is what we're wanting to do. We want to minimize it, so we're going to have to figure out what the radius and the height is. The problem is our surface area formula right now has 3 variables. It has the surface area as one variable, the radius as a second variable, and the height as a third variable. So when we go to do our derivative, we've done derivatives only when we have expressions with 2 variables. And that works well. As soon as we add that third variable, now we run into some problems. So what we're going to do in part A, it's leading you to say, could you rewrite your surface area formula that you have right here so that the height is gone? So it looks like this. Because if you can do that, then you can take your derivative and then you can find things nicely. So how do we go about doing that? Well, we were told something about our volume. Here's our volume formula. We know that the volume that we want is 54 pi. This is designed to work out with nice numbers. Very few cans of Coke say that the volume of this can of Coke has 54 pi milliliters in it. They usually say something like 355 or 210 if those are those, I think those small ones. Well, I don't know if that's 210 or not. Anyways. So now what we can do is we can rearrange this formula and get h by itself by dividing by the pi and the r squared. And the nice thing is those pi's cancel out, so you know that your height is equal to 54 over r squared. So now we can take our surface area formula, which is the 2 circles at the bottom, plus the circumference times the height, and now we can rewrite it by substituting in instead of the height, we know the height is 54 over r squared. And simplifying this, plus 2 times 54 is 108. One of those r's will cancel out. And that matches what we wanted to show. Now, if they didn't have this part A, you would still have to come up with this idea. How could I write my surface area just in terms of one of those variables? Either just the radius or just the height. Because once I have this, I can now go to part B. I'm going to rewrite it. I'm going to write that r on the top as r to the minus 1. It's going to make my derivative a little bit easier. And I'm going to find the derivative. Was that, did I copy it down right? Yes. So we get 4 pi r minus 108 pi r to the minus 2. We want to set our surface area equal to 0 to find the minimum. I'm going to move that r squared to positive exponent so you have it on the bottom. How do you go about solving this for r if it was a non-calculator question? What do you do when you have an r squared on the bottom of a fraction? What could you do? If we multiplied both sides by r squared, do you see that that would get rid of the fraction? Now, normally, if you get rid of fractions in a rational equation, that makes your life a little bit easier. When I multiply the left side by r squared, I'm still going to get 0. When I multiply the right side by r squared, it would get distributed, right? And it would multiply each term. So now those r squareds here would cancel. And we now have 0 equals 4 pi r cubed minus 108 pi. We're feeling a little bit nervous because we see an r cubed, but it's not going to be that bad because there's just an r cubed. We can move everything over to the other side. 108 pi equals 4 pi r cubed. Divide by 4 pi. (108) divided by 4 is 27, and the pi's cancel out. And I said this had nice numbers in it. Take the cube root of both sides, and you figure out your radius has to be 3. It's not plus or minus. It is an r cubed, so we only do the plus or minus if we're doing an even power. And if it was an even power and you did the plus or minus, then you have to say, well, in the context of this question, it's very hard to make a can with a negative radius. I don't know, that would be like some sort of black hole. You'd get sucked into it. I'm not sure. It wouldn't be a pleasant experience. So that's why they haven't designed those yet. So we get a radius of 3. Were there units involved here? Checking before, was it centimeters? So we know that our radius is 3 centimeters. Have we solved the question completely? Sometimes you get so excited that you get to the end, you just skip and go on to the next question. It's always a good thing, especially on an exam. When you're done, read the question again. Have we solved everything we wanted to? We found the radius. It says find the radius and the height, which makes the surface area minimum. So now we still need to find our height. Well, if you go back to part A, we had a formula that height was 54 over r squared. And now that we know the radius is 3, we can plug that in, 54 divided by 9. The height will be 6 centimeters. And now we're done. Now we know that a radius of 3 and a height of 6 centimeters will give the minimum surface area. And it didn't ask us to find the surface area, but we could plug those values into that formula and find out what that minimum surface area would be. So now you could do this same question. The numbers won't work out as nice, but you could figure out that can. Can of Coke has 355 milliliters. Okay? As far as measurements go, do you know that 1 milliliter of water is 1 cubic centimeter of volume? Coca-Cola isn't water, but it's pretty similar as an item. So as far as volume goes, a can of Coke takes 355 centimeters cubed. They probably have to leave some space for air in the top, but not a lot. But theoretically, you could now figure out, is the design that they have for a can of Coke the right design for the maximum cylinder. Okay? If it's not, what might be the reason for that? And you've seen a can of Coke. It's not a perfect cylinder, right? They have extra material at the top. They've got the extra material with the tab and stuff like that. So they've probably taken all of that into consideration as well to create the design that would work the best. If you wanted to create the design that would use the minimum materials possible, it would be a sphere. Now that's not very practical though for making a can. Although at Christmas sometimes they had those bottles that were like, so you could use them as ornaments. Like I'd like to hang a bottle of Coke on my Christmas tree. Such a good idea. But yeah, so a sphere wouldn't be that good as far as, you know, you put it on your table and spill it again and again and again. So that is part of the problem. Other problems with spheres is they don't pack very nice. Cylinders pack in boxes very, very, very nice. So, and they don't make cylinder boxes to send out things. So it's not very practical. So we've got all of these things involved. And sure enough, there's someone who has thought about these things to make them a minimum. Because for Coca-Cola, making 1.6 billion cans a day, 1.8, thank you, that little amount is going to save them millions and millions of dollars. So they're willing to pay a mathematician, you know, here's $200,000, make this better, to figure that out. What am I, so there's the end of that. We'll start related rate questions.